All right, we're back to talking about rectangular waveguides, and this is the slide that I put up that shows the distribution of field inside the rectangular waveguide, and just for various modes. And so recall that TE10 is the dominant mode when A is greater than B, so in other words, the width is greater than the height. The dashed lines are the magnetic field lines, the solid lines are the electrical field lines. And when we're looking at a slide here in a bit, I just wanted to point out in this particular example, this is a cross-section of the waveguide. So basically the wave will peak in the middle and go to zero at the walls as far as the intensity if we look in the horizontal direction. Here, notice in the TE20 mode, we have two peaks, one here and one here. If we're looking at the intensity, if we're looking at the magnitude, then we would come up and we would come down. But basically looking at the field intensity, we have peak and peak. And the reason to point this out is that when we look at how to excite waves in a waveguide, we'll see that there's one antenna used in this case, placed right in the center of the guide. In this case, we would have two antennas, one here and one here. And then there are just some other mode distributions shown on this page. All right, so in practical considerations of waveguides, the first thing to think about is how we get the energy in. So this is an example. If you look right here, this is what we just looked at, where in this case you would have the TE10 mode. You'd have a single cross-section, a single half sinusoid for intensity, where the peak occurs right here in the middle where the antenna probe is placed. Here would be the two probes exciting this mode and this one. For a TE11, you would have this configuration of antenna as being most efficient, and for a TM11 you would have this kind of antenna arrangement. So basically you design the antenna to introduce a field with a geometry that's consistent with the desired mode. Now that doesn't mean that if you try to excite a TE20 mode, you won't eventually get some mode mixing and mode degeneracy. You'll have some TE10 that'll eventually mix in, just because that is just the nature of the beast with waveguides. All right, here's a cross-sectional schematic of what the antenna probe looks like. You typically will bring it into right at the center of the guide. Typically, your coax connector is a 50 ohm connector, and your waveguide is some other impedance, usually 200 ohms plus or minus. So if you bring this antenna in on the back, so this is like taking this and rotating it 90 degrees. So on the back side, you would put a short at some distance D, and then D can be optimized for your particular design, and then the waveguide proceeds in this direction. So because you have this impedance mismatch, these systems have little tuning screws in the side that has a little stub of a screw that comes into the waveguide itself. That helps you to experimentally match the impedance. You can also have tuning in the form of how far back is this short, which also enables to help with impedance matching. The lower TE01 cutoff occurs when the dimension's about a half wavelength in free space. So at the center of the band, your wide dimension's about 3/4 of a wavelength, narrow dimension's about 3/8 of a wavelength. Typically, the probe is about half of the distance on the narrow dimension, so it's typically about 3/16 of a wavelength. That can be manipulated as well in order to get good results. With good simulation software now, we are able to get much better design before fabrication, but even then there's some experimental tuning that goes on because it's just very hard to effectively simulate all of this. Here's a photograph showing the coax connector. So this would be the actual picture of what's going on up here. just 3 different ones from 3 different perspectives. And so your coax screws in right here at the top. The other practical consideration is mode selection and excitation. Typically, you do want to only propagate a single mode. This avoids mode dispersion. You might remember mode dispersion is going to occur because different modes will have different phase velocities, as well as mode degeneracy, which is when different modes propagate when you have more than one mode that's there below cutoff with the same wavelength, but if it's a square waveguide, you might recall that your TE01 and your TE10 modes will be the same. So we'll have the same cutoff. So the design rule of thumb is to make the ratio of A over B equal to 2. And in that case, the cutoff wavelength in the guide is 2A over this factor involving M and N, which are your mode numbers. So for 1, 0, you'd put 1 in for M, you'd put 0 in for N, and basically your wavelength, cutoff wavelength then would be 2 times the dimension A. So that A dimension is a half wavelength. Okay, so here is a figure that we showed in class. We were looking at the TE10 mode as having the lowest cutoff frequency being the dominant mode. And so basically within this waveguide, to stay at the dominant mode, you want not to run in as you come up on frequency. As you come up in frequency, you don't want to run in and pick up any other modes. So if you come over here to 2, you'll notice that at A over B ratio of 2, you basically can come all the way up to pick up the TE20 mode, so you can have a frequency band that's fairly wide at 2, and you don't really get any returns at 3 because you're still running into this TE20 band, which is flat. So really the ratio of 2 to 1 is about optimum. The reason you don't want to go bigger is pretty much a practical reason, just the cost of copper. So some additional considerations, just as far as design rules of thumb. When we propagate a frequency band, the guide dimension A should be about 0.7 times the wavelength of the center of the band. If you get too close to the wavelength, you allow for the possibility of the introduction of higher modes. So in other words, if you get at the top of the frequency range here, it's possible, if your waveguide design isn't perfect, that you pick up some of that TE20 mode. So you want your design to be right in the middle of this bandwidth. Now, how do we get the energy out? Basically, we get the energy out by transitioning from the waveguide impedance to the impedance of air, if you're introducing this wave into air. So this is done with an antenna. This is referred to as a horn antenna. There are all different kinds of geometries of horn antennas. This one is just it meets the rectangular guide, and then it comes out and transitions to a bigger rectangle. You can have these that transition into a square. Some of them transition into a cylinder. And so basically you do get, right here at the antenna, you get quite a bit of mixing of the pattern of your field. It doesn't come out exactly the same as what it is in the waveguide. That's usually okay, because usually the goal is to just deliver this energy to a load that's usually fairly close to the antenna. So it's usually not an issue. People put all kinds, the biggest issue usually is how do you get your energy out without reflecting it back into the guide and ultimately back to the magnetic supply, the magnetron, or whatever you're using to create your microwave field. So, so this just has the effect of grading that mismatch, so that if you do have reflections, they're usually occurring in this antenna, and the geometry is such that they can, interestingly enough, often be kind of redirected back out. So the horn antenna is used for that region. Now, as I was saying, if you look at commercially available ones, you'll see some that have vanes, looks like a little, almost like a windmill vane that that sticks out from the sides. Some of these will have little ridges. Some of them, instead of a continuous change, will have little step changes. So there've been all kinds of design of efficient, all kinds of introduction of kind of unique designs of efficient microwave antennas. None of them are perfect, but they do have some interesting geometries. All right, at this point, in order to keep the video fairly short, this concludes, I believe, the material that we talked about in class the last time class met. So we will end the video here and create a new video for the material that we did not cover in class.